Darpa is taking a counterposition to Newtonian mechanics and building a motor that operates in complete silence. It's based on electromagnetism, which is the unification of electricity and magnetism into a single fundamental force by conceiving light as a wave and not as a particle. The idea that the concept can be practically applied in the motoring world is making waves after the Defense Advanced Research Projects Agency announced its breakthrough in naval propulsion, a system with no moving parts. DARPA puts its energy into magneto-hydrodynamic technology. DARPA is heading for a breakthrough by applying electromagnetism to naval propulsion, aiming for a configuration with no moving parts whatsoever. This translates to, in theory, a completely silent ride, except for water disturbance, which is minimized with clever hull design. Instead of moving parts, the system will operate on MHD, magneto-hydrodynamic drives, replacing naval propellers with magnetic fields and an electric current. DARPA is the research and development agency of the United States Department of Defense, responsible for the development of emerging technologies for use by the military, and it has recognized the implications of being able to move through the sea undetected. The applications for stealth submarines are certainly worth pursuing, and the United States would be the first country to look to magneto-hydrodynamic tech, at least that we know of. DARPA's pump program, DARPA's ultra-quiet magneto-hydrodynamic drive, works on superconducting magnets that produce triple the efficiency of what similar drives have managed to achieve until now, and it's developing these under the pump program, Principles of Undersea Magneto-Hydrodynamic Pumps. The main aim is to solve a critical electrode materials challenge and facilitate a more efficient, reliable drive. There are three main steps to achieve this. Creation of a modeling and simulation design tool. This needs to be able to assimilate electromagnetic, electrochemical, and hydrodynamic factors. Determination of a suitable electrode. This component needs to be reliable. It must have a workable lifespan, and it must function well over prolonged use. Design and manufacture of a prototype. This stage will hopefully validate the simulations and choice of electrode material. Magneto-hydrodynamic drives are not new technology. Over 30 years ago, the Japanese developed a functioning magneto-hydrodynamic drive and successfully powered a 100-foot, 30-meter ship called the Yamato 1. It proved an efficiency rate of 30% and reached a top speed of 6.6 knots on a magnetic field strength of about 4 Tesla. The commercial fusion industry is well aware of what advances in magnetic technology could yield. Rare earth barium copper oxide (REBCO) magnets are reaching magnetic field yields as high as 20 Tesla, a level that has the potential for 90% efficiency in a magneto-hydrodynamic system. The electrode materials challenge magneto-hydrodynamic drives have problems with corrosion due to gas bubbles that form on the surfaces of electrodes when a current, a magnetic field, and seawater interact. This reduces the efficiency and output significantly, and it takes place relatively quickly. The pump program is trying to develop durable military-grade electrode materials to reduce erosion and hydrolysis. Applications of magneto-hydrodynamic propulsion for the Navy. There are two main benefits of MHD technology for defense and warfare. Tactical techniques. MHD drives have almost no vibration or noise because there are no moving parts, which would make submarines or drones difficult to detect using sonar and increase stealth capabilities, speed, and maneuverability. In theory, MHD drives could generate faster propulsion and greater maneuverability, as they can exert force in any direction. It remains to be seen whether DARPA can get beyond the problem of sourcing electrode materials that don't corrode. However, if it can, the defense forces of multiple countries will start paying attention very fast.